Hello everyone, welcome back to my channel. So quantum computation and quantum information has become a large field over the years, and the number of qubits that people can construct increases from 2, 3 to around 50 qubits nowadays. And recently there are many exciting news in this field. For example, Google and NASA claimed to have demonstrated quantum supremacy on a general superconducting quantum computer over a classical computer. So it is a thriving field, and a lot of money gets into this direction. However, as a general public, or someone who is not in the field, it feels that quantum computers are actually still far from us, because you know that usually those superconducting qubits can only operate at 15 millikelvin, so you need a large equipment to cool it down, and also there are only a few quantum computers in the world. It feels that it is a very far reach, but actually this is not the case. Actually, you or anyone in the general public can use the quantum computer, can use the state-of-art technology of this quantum computer. So this is basically the IBM quantum computer that they posted on the internet, and it is a general quantum computer superconducting structure, and I think now they offer 5 to 14 qubits quantum computer online. And the nice thing is that it is freely accessible to the public. You just go to this website, and then you can use the quantum computer. So to program the quantum computer, there are two possibilities. One is visual programming, similar as the LabVIEW. Use this circuit composer. If you want to write lines, write programs, you can use this Qiskit. It is a notebook style. So I guess if you are a quantum scientist, you are in this quantum computation field, you may be more used to this circuit composer, because usually the quantum algorithms are written in the language of this circuit. But if you are some guy from the open source community, some programming, maybe you would like to learn this Qiskit. But I think this circuit composer is anyhow a good way to start. Okay, so if you log in the IBM Q Experience, and this is basically the window that we will see. On the right hand side, you have different backends. So basically, those are the available quantum computers for you to use online. On the left hand side, that is the menu. If you move your mouse onto the menu, it will expand, and you will see the details. And what is important is that the center icon there is actually the circuit composer that I mentioned in the last slide, and we will use in this circuit composer to build our quantum circuits. Here, those are the tabs, and those are the recent files that you construct. And down there are the results of the calculations. So if you hand in the job to the quantum computer, it will wait in the queue until it is executed, and then the final result will be shown in the latest results here. So if you go into the circuit composer, it looks something like that. And the important thing is that those lines here, those are the workspace. So each line corresponds to 1 qubit. There are 5 lines here, and those are 5 qubits. So Q0, 1, 2, 3, 4, 5 qubits. And this 0 means that, so you know that the qubit has 2 states. Yeah, so either it is 0 or 1. But different from a classical bit, qubit can have the superposition of 0 and 1 state. Yeah, but usually we first initialize everything to 0 state. And you see that there is another line here. Basically, that is the measurement output. Yeah. So before the measurement of the quantum state, you know nothing about the quantum state. So you have to measure it and give the output to this line so that we can analyze the quantum state. You see that the y-axis is actually the index of the qubits, but the x-axis along the line is actually the time. So if you go from the left to the right, the time increases, the time passes by on each line. Those are the workspace. What can you do in this workspace? You can have operations on single qubits, on 2 qubits. Yeah. So those are the operations available. Yeah, each icon correspond to one operation that you can just click here and drag to the qubit that you want to apply. It's very simple. And those operations we usually call it gate. The last important thing is that we need to measure the qubit, and that's this icon. You drag this icon here, and then it will measure the qubit and connect it automatically to the measurement output. Yeah. Okay, so what are the available qubit gates? What operations can we do on qubits? There are generally 2 categories. One is single qubit gates, which only act on a single qubit, and 2 qubit gates. We have basically infinite number of single qubit gates, but one of the most important one is this so-called Hadamard gate. If you input 0 state, it will be transformed into 0 plus 1 over square root 2. If you input 1 state, it will transform to 0 minus 1 over square root 2. So this is important because it creates superposition of 0 and 1 state, and superposition is one basic and important ingredient of quantum mechanics and quantum computing. Another possible single qubit gates are Pauli X gate. Basically, it flips 0 and 1. And then Pauli Z gate, which add a minus sign on the 1 state, but you can also find some other single qubit gates. The power of quantum computing also relies on the fact that we can entangle the qubits, and for the single qubit gates we can never result in the entanglement. So we need some gate that operate on 2 qubits. It has been shown that any logic quantum gates can be written as a combination of single qubit gates plus the C0 gate. So actually we only need one 2 qubit gate, which is this so-called C0 gate. So what is the C0 gate? So C0 gate stands for controlled NOT gate. So it means that we have a controlled qubit here, and we have a target qubit. If the controlled qubit is 0, we don't flip the target qubit. So if the target qubit is 0, it still remains 0. If it is 1, it remains 1. If the control qubit is 1, then we flip the target qubit. So basically, if it is 0, then we change it to 1. If it is 1, we change it to 0. That is what I write here. We say the first qubit is the controlled qubit, and the second qubit is the target qubit. And 0, 0 goes to 0, 0, 0, 1 goes to 0, 1, because the first qubit is 0. So we don't operate on the second qubit. It remains the same. But if the first qubit is 1, then 1, 0 goes to 1, 1, and 1, 1 goes to 1, 0. Then we flip the second qubit. And in this case, we create entanglement between the control qubit and the target qubit because now they are not independent of each other. Yeah. So with this Hadamard gate, we create superposition, and with the control NOT gate, we create entanglement, which are the 2 fundamental important ingredient. And we will show later that this is actually very powerful. Okay, so with that, we can already build some test circuits on this quantum computer. So the first circuits is very simple. It's just a superposition of 0 and 1 state on a single qubit. We know that we start with a 0 state, and after this Hadamard gate, it goes to 0 plus 1 over square root 2. And then if we do the measurement on this state, like one measurement will only result in one result. So either it is 0 or 1. But for a quantum measurement, it is probabilistic, and we can do the measurement for, let's say, 1,000 times or 3,000 times. And then we see the statistics, and what we expect is that we will see 50% 50% of 1 and 50% of 0. That is because the coefficients before the 0 and 1 is the same. Yeah. This is already something that is quantum mechanical, because if you imagine that you have a classical bit, if it is 0, you measure 1,000 times, it is still 0. But for the quantum state, it is in the superposition state. Every time you measure, you cast the state into 1 possibilities, and in total you will see 50%. And then we can actually add some entanglement. We can add the second qubit and create entanglement between the 2 qubits and generate the so-called Bell state. So after the Hadamard gate, the first qubit goes to the superposition of 0 and 1 state, and then we apply a control NOT gate on the first and second qubit. And you will see that if the first qubit is 0, the second qubit remains 0, yeah? Because the second qubit is initially 0, and if the first qubit is 1, then we flip the second qubit from 0 to 1, and the resulting state in the language of the 2 qubits are 0, 0 plus 1, 1 over square root 2, and this is the well-known Bell state. And then we can do the measurement separately on the first and second qubits. And you know that now we have 2 qubits, so there are 2 to the power of 2 equals 4 possibilities. However, in the measurement, we will only see 2 possibilities, 50% 0, 0, 50% 1, 1, and there is never 1, 0 or 0, 1. And this is because of the entanglement. The most exotic thing is that for the Bell state, what we can do is that after creating the entanglement, for example, we can imagine that we move the 2 qubits very, very far, let's say 1,000 kilometers apart. And then before the measurement of the first qubit, we know nothing about the exact state of the first and second qubit. However, if we measure the first qubit, if it is 0, then we know that the qubit 1,000 kilometers away must be in the 0 state, although we haven't measured it. If the first qubit is 1, then we know that the qubit 1,000 kilometers away is 1. So this is kind of counterintuitive, yeah. But this is very important. And the natural extension is that whether we can include more states and entangle more states. The answer is yes. And this is the so-called GHZ state. Some people also want to call it Schrödinger's cat state. So in principle, it's also quite simple. We add a Hadamard gate to the first qubit, and it turns to the superposition of 0 and 1. And then we use a C0 gate to entangle the first and second qubit, and then we arrive in this Bell state. And then we entangle the second qubit with the third qubit. With a simple math, you will see that it becomes this 0, 0, 0 plus 1, 1, 1 state. And then we can do the measurements. Now you know that there are 3 qubits, and there are 2 to the power of 3 equals 8 possibilities. However, among those 8 possibilities, there are only 2 that actually should exist in the measurement. That is 50% 0, 0, 0 and 50% of 1, 1, 1. So this is also a highly entangled state in the 3 qubit case. But of course, you can also extend this to 4 qubits, 5 qubits. Just add more C0 gates. Yeah. So those are the possible circuits that we can easily build. And in the next few videos, I will actually build a circuit and run it on the IBM Quantum Computer, and I will show you the result. Yeah, so you will see that what I wrote here are purely theoretical expectations, but of course practically, if you run it on the quantum computer, there will be errors, there will be different things. So you will see that in the measurement we will also have other possibilities. Okay, so I hope that after this introduction, video, you're already quite interested in doing quantum computation, in operating this quantum computer by yourself. So if that is the case, I welcome you to my next videos, in which I will show you how to construct this circuits, and how to run the quantum computer, how to analyze the result, and how to see like there are errors. So I highly recommend you to stay with my videos, and also try to do it on your own, because this would be a very nice experience on quantum mechanics. Yeah, because usually you don't have a handle on quantum mechanics in your daily life. Okay, so I thank you for watching. If you like my video, I appreciate your like or subscribe to my channel, and I hope to see you next time.